going over my homemade study guide for SLR1, the structure and the function of a processor for A-level computer science OCR specification. The main components of the CPU that you'll be required to know are the program counter, the memory address register, the address bus, the RAM, decode unit, accumulator, arithmetic logic unit, memory data register, data bus, current instruction register, cache, control unit, control bus, how they all interact within the CPU. The control unit. The control unit sends out signals to coordinate how the processor works. It controls how data moves around parts of the CPU and between the CPU and memory. Instructions are decoded in the control unit. It essentially controls the whole CPU and the function of the processor, so, i.e. that's where its name comes from. It controls by the orange lines in this model, and it directly communicates using the control bus. The program counter. The program counter keeps track of memory locations on the line of machine code being executed with each iteration of the fetch decode execute cycle. It gets incremented to the point of the next instruction, allowing it to be executed in sequence, instruction by instruction. The program counter can also be changed by instructions that alter the flow of control, for example, like branch back to 0, branch to positive, etc. But it's incremented by one basically for every single step of the flow of instructions. And it also holds the address for the next instruction to be executed. The memory address register. This holds the address of the memory location from which data or an instruction is to be fetched or to which data is to be written. It is really important, and it's mostly used in the fetch part of the fetch decode execute cycle. Memory data register. It stores the data or instructions that are to be fetched from or sent to memory, as seen here in orange. It interacts directly with the data bus and RAM. The current instruction register. It stores mostly fetched instructions which will be decoded and executed. It is basically where current instructions are held in a holding place while they wait to have the next thing happen to them. The instructions also contain opcode and operands, which we'll go over later, and they came from the memory data register usually. The arithmetic logic unit. The arithmetic logic unit basically carries out all the calculations and logical decisions within the CPU, and its results are stored in the accumulator. So the arithmetic logic unit does like and, or, etc., addition, subtraction, multiplication, division, basically all the mathematical things, but also logicals in that sense. And then when it is complete, it's stored in an accumulator, which is basically a general register. Just think a bit like that, just a general temporary storage to hold calculations. But it can also be stored in general purpose registers if the accumulator is full or whatnot. The accumulator stores the results of the calculations made by the arithmetic logic unit, as we went over, but it can also be replaced with general registers, buses. There are three buses that we need to know about. The data bus. It carries data between the processor and memory. This is directly connected to the data register. The address bus carries the memory location to be read from or written to, connected to the memory address register. The control bus sends signals from the control unit to RAM, the main memory, as shown in the model. The fetch, decode, execute cycle. We start by fetching, then decoding, and then executing. This is a critical part of our specification, and you need to know it, and you need to know how the CPU interacts with this. So the program counter are then sent to the memory address register. The contents of the memory address register are sent along the address bus to the relevant address. So you see here 000 to 000. Meanwhile, in the control unit sends its what is in it along the control bus. The contents of the memory location stored at the respective area, in this case 000, are then sent across the data bus, which is two-way, to the memory data register, as you can see here. And then the contents of the memory data register are copied to the current instruction register, which is here, where they are temporarily stored. And then the program counter is incremented by 1, as one cycle for the fetch, decode, execute cycle has been completed. Because there's the fetch, decode, execute cycle, the contents of the current instruction register are sent to the control unit. In the control unit, they are decoded, is sent to the decode unit, where the control unit decodes the instructions, like contents of memory location, CPU, accumulate, etc. This is where the parts of the instructions are 8 bits usually, and then the opcode is what we want what to do, and then the operand is what to do it to. So what to do and then what to do it to. So the execute phase of fetch, decode, execute cycle. This really depends on what happens. So if the value is being inputted, the accumulator will store the value. If the value is being outputted, the value currently in the accumulator will then be transferred on. If the value is loaded from RAM, this will be sent across the data bus from RAM to the memory data register. If the value is to be stored, it will take the value from the accumulator, send it to the memory data register, and then send it across the data bus to RAM to the correct location, address location in the memory address register. If the value is to be added or subtracted from another value, the values will be passed to the arithmetic logic unit, the operation will be carried out, and the result will be stored in the accumulator. If the little man computer code is to branch, etc., any branching, the comparison will take place in the arithmetic logic unit. Factors affecting CPU performance. So there's the big ones are going to be clock speed, number of cores, amount of cache memory, and use of pipelining. Sometimes in some exam questions it will say one and say some others, or it asks you to elaborate on that one, or just say to sometimes just list it. So clock speed, it's measured in hertz, the number of cycles per second that like the CPU can take, and modern processors process at billions of cycles per second, kilohertz. So that is, so the more hertz it can do, the faster it will be, and you really want to be in the giga, or essentially, because that's where we are nowadays. Cache size. Cache is the temporary storage of data and instructions to be read and written from. It's located near the CPU, and it stores copies of recent data and instructions. It's much quicker to access to RAM than RAM because it's connected to the CPU, whereas RAM is a separate thing and it has to travel through the buses, where this is connected directly to the CPUs, making it a lot faster. That's a really key component. We want to avoid getting instructions and data from memory if we don't need to, because it costs us a lot of time, like I said. So that's why cache can be really important. Larger cache size or more cache can really increase the CPU performance. The number of cores. A core is a very simple term. In simple terms, is a copy of the CPU. So a quad-core processor would have 4 separate process units, each with its own registers, arithmetic logic unit, accumulator, control unit, etc. They're basically mini CPUs, and they all work together in that sense. With CPUs with more cores, we'll have more power to run multiple programs at the same time, but not always. The more cores, the more powerful it is, because certain things don't allow for multiple core use, etc. Many programs are not designed for multiple cores, like I just said, so they can't make use of these multiple cores, so it can be a waste sometimes, but a lot of modern programs are designed to use multiple cores, because For example, the computer I'm using now is an Intel Core 17 i7, my mistake. And pipelining. Pipelining is a technique that can be used to improve performance. Basically, by using pipelining, the next instruction can be fetched while at the same time the processor is performing other functions. So basically, in the it will start by, if you can look at the model, the instruction one is here, and then step two, instruction one is in the next part, and while the fetched in instruction two, then instruction one moves on, instruction two moves on, instruction three moves on. So they're all getting processed at the same time, and then so on and so forth. But then if there's branching, you have to start all over again. So you can see in this one, so it's going really well. Oh, but then it says like branch at instruction 3 to 6. So instruction 6 goes in there, and then it just starts moving on there. There's basically a few different types of pipelining. So there's instruction pipelining and arithmetic pipelining. Instruction pipelining consists of various stages of instructions that move through a processor, while arithmetic pipelining consists of the parts of the arithmetic operation that can be broken down, overlapped as they are carried out. Pipelining is very common in modern processors, allowing for multiple instructions to execute simultaneously. So the von Neumann architectures, these will also commonly come up in questions, so as well as the Harvard architectures. So the von Neumann architecture is shared memory space for instructions and data. Instructions and data are stored in the same format. A single control unit or processor follows a linear fetch decode execute cycle, one instruction at a time. So often not using pipelining in that sense. And the registers are used as fast access to instructions and data. So there's like system bus, you can see it's basically there's a separate CPU and then there's separate RAM. And memory space for instructions and data are stored together. Harvard architecture. So this is another form of architecture for processors. The instructions and data are stored separately. That's a key difference between the Harvard and von Neumann. So Harvard, they are stored separately, while in von Neumann, they're stored in the same. They each have their own bus, and reading and writing data can be done at the same time. So it allows for pipelining, and it's often used by RISC processors, reduced instruction set computers, which we'll be covering over later. Contemporary architecture. So modern machine architectures are known as contemporary architectures. The way contemporary architectures are improved are by simultaneously multi um, th th threading, out of order execution, branch prediction, variable clock speed, and power conservation. This is beyond, those things are beyond our specification, but we might need to like just list like how our contemporary architectures improved. But we don't really need to elaborate on them any further. Some forms of contemporary architectures would be single instruction media data, where parallel processing is where it carries out single instruction where multiple data items at the same time, often used by graphic processors, or multiple instructions, multiple data. Another version where multiple instructions are carried on a multiple data items across several cores, or distributed computing. This is basically where computers are on a shared network and they solve a bigger problem together, kind of like crypto mining, if you understand that means. It's been used by NASA to help people process mathematical issues and things at home so they can spread the power and it's not all and costs, so it's not all weighed on one person or institution.